Hello and greetings to you all. My name is Rayendra and this is Djuned. And today we'll be presenting about our research titled Modification of the NSTAR Ion Thruster Accelerator Grid Aperture Diameter to Increase Specific Impulse. First of all, I'd like to explain what an ion thruster is. An ion thruster is simply a thruster that uses ionized gas as a propellant. In this case, xenon gas was used because xenon is inert, has a small ionization energy, and has a hefty mass. The gas will then later be ionized through a process called electron bombardment, where the xenon atoms collide with electrons to produce ions. These ions will then be filtered and accelerated by the screen grid and the accelerator grid, respectively. After being accelerated by the accelerator grid, the ions are shot out of the thruster. Newton's third law then followed. The action of shooting out of the ions resulting in a reaction of the thruster and spacecraft being shot in the opposite direction. On another note, the Near Horizons probe sent by NASA to study Pluto took roughly 9 years to reach Pluto, even with the help of Jupiter's gravity. This probe was launched using a conventional combustion thruster rocket, the Atlas V. It was equipped with thrusters to correct its trajectory, but other than the initial boost from the rocket and the boost from Jupiter, it had nothing propelling it forward. An ion thruster attached to one such space probe would allow it to keep accelerating during its trip and reach its target faster. We hope that by utilizing ion thrusters on future probes, we can thus explore space even further and faster. One usage of an ion thruster happened on October 24, 1998, where there was a mission called DS-1 or Deep Space One. On that mission, an ion thruster was used on a satellite. It produced a thrust of 93 million newtons and a specific impulse of 3,100 seconds, with a propellant efficiency of roughly 90%. That thruster is the base of our research, and we seek to improve its specific impulse by modifying the diameter of the aperture of the accelerator grid of that thruster.
For our methodology, we combined 6 different equations pertaining to specific impulse, propellant efficiency, beam current density, total voltage, and accelerator grid voltage. The last equation has the diameter of the accelerator grid aperture as an independent variable. Combining these equations leads to the giant equation seen on the slide. We've all seen values being constant except for ISP and dA, which are a specific impulse, and the diameter of the apertures of the acceleration grid, respectively. From the data, it can be seen that as dA is expanded, ISP continuously increases. The increase seems largely linear. From looking at the graph, it can be seen that an increase of ISP against dA is actually exponential. The data also seems to suggest that the less diameter, the closer the ISP gets to around 2 times 10 to the power of 3 seconds. From the data, it would be intuitive that to maximize the ISP, it would work to just keep expanding the dA. However, since mu-UD, or propellant efficiency, cannot exceed 100%, it is thus found that the maximum dA to the highest millimeter does not result in mu-UD exceeding 100%, is 2.44 millimeters, resulting in an ISP of 3,948.06 seconds. This is an improvement of 27.41% compared to the original NSTAR thruster used on the Deep Space One. It is also equivalent to 102 millinewtons. These are our written conclusions, and these are the potential future works which can be based on our research, including comparing the cost of the modified NSTAR ion thruster and the next ion thruster, which is used on the DART mission, and the effectiveness of the modified NSTAR ion thruster if it were used on the DART mission, which is a mission meant to redirect asteroids using satellites. And these are our references. Thank you for watching.